Today we are taking a look at another type of function. We spent a lot of time so far on exponential and linear functions, and now we want to talk about quadratic functions and see how they fit in the mix. So I've started us out here with sort of a review of those other types of functions that we've already talked about. So we're going to take a look at these tables of values and see if we can figure out which type of function they each represent. So in this first one, and I mean, feel free to pause the video and think about it yourself first if you would like to. But I am noticing that this is increasing steadily by adding 4. So this is repeatedly adding 4 over and over again. I mean, that pattern continues. I'm not going to write it out all the way. But remember that constant addition would indicate that this is a linear function. And because the x's are increasing by 1 each time, that would tell me that my slope was equal to 4. Alternatively, this one, if you look at how they're increasing, if you're thinking about this in terms of addition, we're adding 12, but then we're adding 24 to get from 24 to 48. And so instead, I hope that you recognize that this is multiplying by 2 each time. And that pattern does continue. We can verify that. And so this really shows us that we have an exponential function here. And again, because the x's are increasing by 1 each time, that would tell us that the b value is that constant multiplier of 2. Okay, now when we go to this one, though, I'm not seeing a steady pattern of either addition or multiplication. And so let's talk about what's happening here. So to get from 2 to 3, we're adding 1. To get from 3 to 6, we're adding 2. Nope, we're not. We're adding 3. Sorry about that. 6 to 11, we're adding 5. 11 to 18, we're adding 7. And then 18 to 27, we're adding 9. Okay, so not a constant growth, but there is a pattern here, right? Like we could predict what this next value is. It would be adding 11 onto that 27, okay? So let's take a look at this row of numbers and kind of approach it this same way. And you'll notice that what's happening here every time is that these differences are increasing by 2. So this is called having a constant second difference, okay? That the second round of differences, not the first round was right here, but the second round came out to all be the same. That indicates that this is a quadratic function. And a quadratic function is one that has an x squared in it. We'll talk about that down here. We've got a definition of quadratic here. This 2 doesn't really tell me anything about the function. Like up here, the 4 told me the slope, the 2 told me the growth factor. With a quadratic, it's just the fact that these values are all constant, right? These values are all the same. So this is called having a constant second difference. And that indicates that the degree of the function, which we haven't actually talked about degree, but that just means the largest exponent in the function that we're trying to write is 2. You're going to see this when we talk polynomials later on, that if it took 3 rounds, for example, to get to a constant difference, that would mean that we have a cubic function. We have a degree 3. If it took 5 rounds, we would have a degree 5. So we will be coming back to this idea, but for right now, we're just looking at quadratics as a possibility. So if neither linear or exponential is working out, give this a try and see if you've got a constant second difference. Because if you do, that means you're looking at a quadratic function. So what is a quadratic function? You did learn about these last year in Algebra 1. Function with a degree of 2. Degree of 2 just means the function has an x squared in it. And that x squared is the highest exponent. So there's nothing bigger than a square. Okay, this is what the general form looks like. I'm sure you're familiar with this, but this would be like something x squared, something x, and something. I don't know why this is going in and out so much. So this is an example of a quadratic, right? Where the a value is 1, the b value is -2, and the c value is -3. Now, later this week, we will be talking more about how to work with these mathematically and how to solve for some of the things we're talking about today. Today, my biggest concern is just that you understand vocabulary. So there's kind of two things that we care about with quadratics. First is the spots where it crosses the x-axis. You may know those as x-intercepts, but we're going to call them roots. Okay, and so there's two roots in most quadratics. It is possible for there to only be one root if that quadratic is just sitting right on the axis, and also possible to have no real roots, which would be when the quadratic doesn't touch the x-axis at all. But we'll be exploring all of those as the week goes on. And then this point down here, this is the vertex. And just to get us used to this, the letters we use to represent the vertex are h, comma, k. Okay, so the vertex, the coordinates of the vertex are h, comma, k. Okay, so let's talk about these a little more in general. Like I said, today's lesson is really general about quadratics, and then eventually we'll learn how to solve for roots and solve for the vertex and all of that. But let's just nail down some properties here. So the domain of any quadratic, if you think about that graph of that parabola that I just drew, a parabola is always going to stretch out forever, left and right. So your domain is always going to be all real numbers. Okay. Now, these next three all kind of tie in together, and for all of them, we need to know what the vertex is. Sorry, I don't know why it seems to be like zooming in and out here for you, so sorry about that. We need to have a vertex, so I'm just going to put down what we had before, h, comma, k, and again, we'll learn later this week how to solve for that. Your parabola could be facing upward, like this, or it could be facing downward, like this. That, by the way, is all controlled by the a value. So you remember that general form that we talked about, that number in front of the x squared, if it's positive, you've got the smiley face parabola, right? If it's negative, you've got the frowny face parabola. And so depending on which way your parabola is facing, that's what determines whether you have a minimum or a maximum, okay? So, and I guess I could have written this over here by the minimum or maximum, but we are going to have a maximum at the k value if a is less than 0. So if the a is smaller than 0, if the a is negative, you're going to have a maximum, and that maximum value will be whatever k is. You will have a minimum value at k if a is positive, okay, because that's this situation here, okay? And then the range is kind of an important one too. That also relies on knowing this k value, because if you think about where your y values are, if your parabola is facing upward, it's going to be everything above whatever that k value is. If your parabola is facing downward, it's going to be everything below where that k value is. So for my range, I would say all real numbers greater than or equal to k if the greater than would be when, you know, the vertex is at the bottom. So that's when a is positive. And all real numbers less than or equal to k if a is negative. Now, that's a lot of like ifs, that's a lot of separate things to kind of remember. I would not try to remember it. I would make sure this makes sense to you. If you know whether your parabola is facing up or down, you should be able to figure these things out just from that. So I wouldn't waste a whole lot of time memorizing this. We're kind of just talking through it so that you understand, like, that's a decision you have to make. Okay, the x-intercepts. These are also known as the roots. So I'm just going to put in AKA roots. And anytime you're looking for x-intercepts, no matter what type of function it is, you're going to put y equal to 0 and solve. And I'm going to make a note here, even though we're not learning this today, that the solving almost always involves using the quadratic formula. Not always. There's ways to do it without the quadratic formula. But I want you to associate these two things, that roots are found by the quadratic formula. You learned that last year. You're going to learn it again later this week. The y-intercept is when x is equal to 0. And in a standard form quadratic, so like the ax squared plus bx plus c, if you plug a 0 in for all the x's, all you're going to be left with for that y-intercept is the c value. So I'm going to make a note here that, yes, you're plugging in 0 for x, but as a shortcut, it's always at whatever that c value is. Okay, so let's actually look at one of these things and answer some of these questions about it. So we've got this function, negative 2x squared plus 5x plus 3. I'm going to answer a couple of these questions before I graph it, and then we'll use the graph to figure out the rest. We should be able to answer this right now. Which way does this open? Well, the a value is negative 2. So since the a, that's my how do I know, right? A is negative. So this parabola must open down. This is what I'm expecting to see when I graph this thing, is that it looks like this. Okay? Now it says use the function to complete the table below, use the values in the table to confirm this is a quadratic. So literally what we're doing right now is taking these numbers and plugging them in for x. I'm going to use Desmos to do this, and that's going to cheat a little bit because I'm going to be able to see the graph at the same time, but that's just the easiest way to get a table going here. So just to remind you how to do a table here, because I think we've talked about this already, I'm going to give this table a name. I'm going to name it f of x equals negative 2x squared plus 5x plus 3. Okay, no surprises there. That's what we were expecting it to look like. If I would like to add a table, I'm going to hit the plus sign and table. And my x values, this I'm just taking straight from my notes here. Desmos does try to be helpful. It kind of auto-fills for you if it figures out the pattern that you want. And then in place of y1, I don't want to make up my own y values. I want the function to determine my y values, right? I want to get my y values from here. So I'm going to put f of x1, okay? F of x1, that's just because these x values here are named x1. So I'm telling Desmos, hey, plug these x values in. Okay, and you can see all those little purple dots showed up on top of my parabola. I'm going to fill those in on my notes page. I'm not going to flip back there quite yet. We'll talk about that in just a minute. But so negative 15, negative 4, 3, 6, 5, 0. 3, 6, 5, and 0. Okay, while we have the graph up, let's answer the questions about domain, range, all of those things. I'm going to see if I can pull this over so you can see my paper at the same time. Okay, so looking at my parabola there, the graph there to the right, the domain of this thing, I could zoom way out on this graph if I wanted to, and this parabola is going to keep spreading out from left to right. It's going to keep getting wider and wider and wider as I go down. So that's telling me that my domain is all real numbers. Really, for any quadratic, the domain is all real numbers. Now let's look at the range. So for the range, it's all the y values below whatever this vertex point is here. It's everything below that value. So I need to know what the vertex is. Really, I need to answer this question first. I do want to take a minute because don't be fooled by this purple dot here. That's not right at the top. I'm going to zoom in a little bit here. And then the nice thing about Desmos is if you just click right around there, that little gray point will show up. That's my vertex, okay? So I'm going to list down that my vertex is 1.25, comma 6.125. And then for my range, I want to say my y values are always below that, right? This 6.125, that's the highest value this thing is ever going to reach. So I'm going to say all real numbers less than or equal to 6.125. Okay. And then last thing is the roots. So for the roots, I need to see where does this thing hit the x-axis. So again, I've zoomed out a little bit. One of them is highlighted over here, but the other one's not. But once again, if I just click right anywhere on that red parabola, it'll highlight those roots for me. Okay, this one showed up twice because it's also in my table, but I have roots at x equals 3 and at x equals negative 0.5. X equals 3. We are going to talk later this week about how to find these things mathematically, but for now, we're just going to pull them straight off the graph. Okay, one last thing that this question asked us to do, and this is going to be important. I wish I had left you a little more space here, but it said to use this table to confirm that this is a quadratic function. So remember what we started this lesson with those constant second differences? That's what we want to be looking at right now. So to get from negative 15 to negative 4, let's see, I would have had to add 11. To get from negative 4 to 3, I would have had to add 7. You could also be doing this by taking the second number and subtracting the first, right? So 3 minus negative 4 would work. But I'm just kind of counting from one to the other. Here we would have had to add 3. Here we would have had to subtract 1. And here we would have had to subtract 5. So remember, for it to be a quadratic, these numbers don't have to match, these kind of burgundy numbers that I just wrote in, but the next round of that should match. So, okay, to get from 11 down to 7, I would have had to subtract 4. To get from 7 down to 3, I would have had to subtract 4. Again, I really wish I had given you more room. From 3 to negative 1, you guessed it, we had to subtract 4. And from negative 1 down to negative 5, we had to subtract 4. So this is a constant second difference. And that's how I'm verifying that this thing is a quadratic. That on my second round of taking the differences between the terms, it came out to be constant. Okay, that's it for this lesson on quadratics. You've got a short homework assignment today, and we will carry on with more quadratics throughout the rest of the week. All right, hope you have a great day.